Alright, hello class. In this video, we are now leaving the module that is all about series, and now we're going to start using series in various different ways. And the main way that we go about using series is approximating functions with them. So what we're going to start with is approximating functions with polynomials. Okay, so in Calculus 1, you likely learned about linear approximation. Okay, so linear approximation was where a function is approximately equal to its tangent line. Okay, let's say at a, for x is really close to a. Okay, so if you remember, this was basically this formula here, where you would have f of a plus f prime of a times x minus a. So this is the equation of the tangent line, and the function itself is very close to this line when you're very close to a. And actually, when you just plug in a, this disappears and you get f of a is equal to f of a. And then for values really close to a, you get a really or fairly close approximation, depending on the function. Okay, now the natural question here is, can we take this further? Can we get better approximations right, if we maybe use a quadratic instead of a linear function, or if we use a cubic instead of a quadratic? All right, so can we get better approximations if we use polynomials instead of linear functions? Okay, and the answer is, of course, yes. All right, and I want to show you just on a graph here how we can go about doing this. I just want to show the graph first and then show you how we find these. Okay, so here is a graph of cosine. All right, so this is cosine of x here. And if I were to plot the, if I were to plot the linear approximation, that's what this is right here, centered at 0. So all these are going to be where a is equal to 0. But here's the linear approximation. Okay, so as we can see here, sort of close to 0, if I were to zoom in, you can see close to 0, this is actually a pretty good approximation. However, it doesn't take long for it to sort of fall apart, okay? Because around in here is when the approximation starts to kind of stink. Now, if I were to use a quadratic approximation, it would look like this. And now we see that the approximation is much closer to the function for a much longer period of time, right? If I were to zoom in, for much longer, this approximation is really close to our function. Okay, but however, we can see that, you know, just like the linear approximation, it does start to get kind of terrible, and say out here it's just awful. All right. Well, now let's add in another, say, definition here. Let's look at a cubic approximation. So this is a degree 3 polynomial, and we can see that actually it gets even better. And we can zoom in and see that for quite a while around 0, we get a good approximation. And then now I'll do degree, actually, I'm sorry, this was a degree 4, not a degree 3, degree 4. Here's now a degree 6. Okay, it's definitely better for much longer, however, it does get really bad around here. Then here is degree 8. Here is degree 10. And here is degree 12. And we can see here, just in the window I'm in, this approximation is really good. See, if I zoom in here, it's pretty much bang on. Okay? I have to zoom out and get out this way. Okay, now it starts to fall apart. Okay? So, just graphically here, we can see that, oh, all right, if we take the degrees out farther and farther, so this is degree 12, we get an approximation that is closer and closer. Okay, let's look at another example just to kind of show the different possibilities. Okay, so for the second one, we're looking at e to the x, and now we're going to look at, here is the linear approximation, okay, here in the pink. And this, you know, aligns with what you probably saw in Calculus 1. And again, if we zoom in really close here, this is centered around 0. And, you know, it's not a good approximation for very long, but when we zoom in really close, we see it's quite good around 0. All right, so if we zoom back out, all right, and now, so this is the linear approximation. Now I'm going to jump to a quadratic approximation. Now for the quadratic approximation, we can see that it gets pretty bad around here, and then it starts to diverge around here. But around here, it's definitely close, and it's close for longer. Okay, now I'm going to jump to degree 4. And we see, once again, up here, it takes quite a while before it veers off. Here, it still takes it, I mean, here it still diverges pretty intensely. Okay, here's degree 6, and gets a bit better over here. Then degree 8, even better. And in fact, if I zoom in over here, we'd have to zoom in really far to see a difference between these two. Okay, and then finally, this will be, I believe, degree 10 or degree, let me double check my work here. Yeah, degree 10. This is degree 10. And again, if I go back to my original window that I was sort of looking at, you see, we don't have much of a jump here. It takes us a bit further to get out. Okay, and if I put the grid back on, and I look at, okay, so this is pretty accurate in this particular window here. And in fact, on this side, on this positive side, we're real accurate for a long time. Like, really very accurate. It's over here that we start to get the problems and the weird blow up. Okay, so this is the motivation, this is the idea, and the reason we might want to do this is because a polynomial is only multiplications and additions and, divisions. Whereas an exponential is not those things, right? It's a lot more complicated. Or a cosine, for example. So if you were writing a program and you needed a cosine, but you didn't have any trig packages or anything like that, any math packages, but you knew you could program multiplications and divisions and additions and subtractions, then you could use that instead and make a polynomial that would give you a really good approximation to your cosine instead of actually needing a cosine package in your program. Okay? All right, so let's get back to get away from these graphs here and start trying to figure out our approximation. Okay, so these polynomials that we're going to develop are called Taylor polynomials, of course, named after the mathematician Taylor. We'll be talking about him in more detail later. But the idea is with linear approximation, okay, our approximation L of x was, let's say, f of a plus f prime of a times x minus a. And the idea is that f of x is approximately equal to this f of a plus f prime of a times x minus a. And if we were to plug in the a, we get an actual equals because this thing zeroes out. Okay. Now for simplicity, I'm going to center this around 0. All right, so let it be 0 for simplicity. And then notice that here we have equals at a for f and the approximation L. Okay, so f of a actually equals L of a. Okay, so what I want here is when I move to, say, a degree 2 polynomial, so for a quadratic approximation, I want, or I'll say we want, f of 0 to equal, I'm going to call this approximation p sub 2 of x. Okay, p for polynomial, 2 for degree 2. I want f of 0 to equal p of 0, and I want f prime of 0 to equal p2 prime of 0. Okay, so here's what we're going to do. Let's say p2 of x, I'm just going to call it a general polynomial. I'm going to say it's a plus bx plus cx squared, right? Just a standard polynomial. I guess I could have done ax squared plus bx plus c. That probably look a little different. And I want, when I plug in 0, notice that these two things go away, and we want this equal to f of 0. So we'll just set a equal to f of 0. Okay, so let's go ahead and put that in. Actually, let's let's go ahead and replace that with the f of 0. All right, and then we want p of 2 prime, which is going to be well, the f of 0 goes away because that's a constant. It'll be b plus c. Well, it'll be 2cx because we'll bring the 2 down to take the... okay, and we want, when we plug 0 in, to get b plus, well, this will be 0, and we want this equal to f prime of 0. Okay, so our b is equal to f prime of 0. All right, so when we put that in, what we have now is this was basically our L of x. This was our linear approximation right from the get-go. Okay? And now, for the third piece, all right, well, I have that f of 0 matches and f prime of 0 matches. Let's find the second derivative. Well, this piece goes away, and we're left with just 2c. Okay, and we want, well, when we plug in the 0, we get 2c, and we want this equal to f double prime of 0. So this tells me that c is not just f double prime of 0, but f double prime of 0 divided by 2. So our final quadratic is going to be f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 times x squared. Okay, now, and now when I go to construct my P3, I'm going to just go ahead and say it starts looking like this. And then add a let's say constant times x cubed. Okay, and we want f to match p sub 3 at 0 for each derivative. And I'll say each possible derivative. Okay, so I'm just going to skip to the third derivative here. The third derivative of p sub 3, well, that goes to 0. This will go to just the constant, then 0. This will go to this thing times x. Eventually it zeroes out, and then what we'll end up with here is the 3 times the 2 times just the 1, because we'll get the 3cx squared, then the 2, then the 2 times the 3 times cx, and then, so I did leave off the c here. All right? And we want, at 0, this to match up with f triple prime at 0. Okay, so this means that our c is going to be f triple prime at 0 over 3 times 2, and 3 times 2 is actually 3 factorial. Okay, so and I told you factorials would start coming up a bit, because now our degree 3 polynomial to approximate is f of 0 plus f prime of 0 times x plus f double prime of 0 divided by 2 times x squared plus f triple prime of 0 over 3 factorial times x cubed. And it turns out that the Taylor polynomials of degree n, okay, are the sum k going from 1 to n, f, well, it's going to be the kth derivative of f at 0 over k factorial times x to the k, which will be, and sorry, that should be k going from 0. So it'll be f of 0 plus f prime of 0 at x plus f double prime of 0 at over 2 plus f triple prime at 0 over 3 factorial, and that should have an x squared, sorry, times x cubed plus f fourth derivative at 0 over 4 factorial times x to the fourth plus all the way up to the nth derivative of f over n factorial times x to the n. Okay? And this is centered at a equals 0. When a is not 0, well, instead of x's and plugging in zeros, we get this, that Pn is going to be f of a plus f prime of a times x minus a. So that probably looks familiar. That's our linear approximation there. Plus f double prime of a over 2 times x minus a squared plus f triple prime of a over 3 factorial times x minus a cubed all the way up to f, the nth derivative of f at a all over n factorial times x minus a to the n. So all you really do is, instead of x's, you have x minus a's. Instead of f of zeros, plugging in zeros, you're plugging in a. For the most part, I'll say that we always, when possible, try and center things around 0. I think that's hopefully obvious why we do that. Okay, but the general formula here is the sum k going from 0 to n, the kth derivative of f at a, all over k factorial times x to the k. Okay, let's look at an example. Let's find some Taylor polynomials. All right, so let's find the Taylor polynomial of degree 6 for f of x equals cosine x. All right, and that would be P6 that we're trying to find. Okay, so here's the usual way I like to go about doing this. For P6, I'm going to need a lot of derivatives to do this. I'm going to need 6 of them. Thankfully, cosine goes well, it repeats itself. It goes between sine and cosine, multiple times. Now, I didn't say here, but I'm going to say with a equals 0. Okay, I want to center this around 0. There's no reason not to here. Okay, so f prime is negative sine of x, f double prime is negative cosine of x. The third derivative is now sine of x. And the fourth derivative is back to cosine of x. Now, this isn't enough. We need to go all the way out to 6. However, you'll see something happen when we do this. So the fifth derivative is negative sine again, and the sixth derivative is negative cosine. Okay, now we're going to plug 0 in for all of these. So let me move this out of the way, just so I can line these things up. Okay, so f of 0 is going to be cosine of 0, which is 1. F prime of 0, though, sine of 0 is 0. So we're actually not going to have all of our, we're not going to have all of these derivatives that we calculated. We're not going to have all of the terms in our degree 6 polynomial. In fact, the odd ones, every one of them with sine is going to disappear, because at 0, all these sine guys are going to be 0. So really, we can ignore them. All right, so f double prime of 0 is negative 1. Okay, this f third derivative of 0 is 0. The fourth derivative of 0, well, cosine of 0 is 1. The fifth derivative, I'm just going to write 0. And then the sixth derivative at 0 is going to be negative 1. So we don't need these. All right, and this should be the terms we need. So we're only going to have 4 terms. So P sub 6, so the degree 6 Taylor polynomial, okay, of cosine is going to be, will be 1, all right, minus 1, actually, let me write this out. It's going to be f of 0 plus f double prime of 0 over 2 factorial times x squared plus the fourth derivative of f at 0 over 4 factorial times x to the fourth plus the sixth derivative of f at 0 over 6 factorial times x to the sixth. All right, now I skipped the ones that are just going to be 0. Okay, so we'll get 1, then minus 1/2 x squared plus 1 over 4 factorial times x to the fourth, then minus 1 over 6 factorial x to the sixth. All right, and there we go. There's our Taylor polynomial. Now let's see how good of an approximation this is. Normally, with a linear approximation, I wouldn't trust it at, say, cosine of 1. All right, so cosine of 1, if I were to use my calculator, okay, using my calculator, I get about, now make sure it's in radians, about 0.5403, blah, blah, blah. If we use P6, this polynomial here, let's see what we get. Now, you can actually plug factorials into your calculator. Each calculator, it's different. I know on the TI guys, yeah, I think it's in your math menu. Yeah, in your math menu over in probability. But in different calculators are going to have different ways of doing this. So I'm going to plug this in my calculator and see what I get real quick. Okay, and since we're only plugging in 1, it really just comes out to be 1 minus 1/2 plus 1 over 4 factorial minus 1 over 6 factorial, which comes out to be 0.54027 repeating. And this is much better than the linear approximation, because linear approximation at 1 would give us just 1, which is way further off than this one gave us. In fact, we can check the absolute error. And this is just a reminder of, you know, a Cal 1 kind of thing. The absolute error is you'll take your cosine of 1 and subtract the p6 of 1 and see what you get, and it tells you how far off you are. We should be fairly close. Right, and in my calculator, this came out to be about 2.45 times 10 to the negative 5. So, all right, which comes out to be about 0.0000245. The reason we use the absolute values is just so if you get a negative number, it just ignore the fact that it's negative. We're not worried about that. This is just telling us how far off we are at 1, and this is pretty darn good. We're accurate within 4 decimal places, and the 5th one we're off by about 2 millionths or thousandths or whatever that would end up being. Okay, so really a pretty good approximation, where the linear approximation comes out to be about 0.46. So we're about 0.46 whole units off. So we're almost a whole half unit off. Whereas here, we're accurate to 4 decimal places. Okay, so we're going to look at some more examples in the time we have left, but this is the general gist of it, and hopefully shows how good these approximations actually end up being. Okay, so here's an example where we can't anchor it around 0, mainly because if f of x is equal to 1 over x, and we want to find the Taylor polynomial, we can't center it around 0, because plugging in 0, we get garbage, and then for every derivative after this, we get more garbage. So, we're going to find this with, let's use a equals to 1. All right, so if we can't use 0, we're going to want to use 1. We're going to want to use things that play nice with whatever it is we're doing, or just the nicest numbers we can come up with. So it's usually 0. If it's not 0, then we'll have to begrudgingly use 1. Okay, so let's find the derivatives. F prime, so the derivative of 1 over x is negative 1 over x squared. Okay, now that's negative x to the negative 2. Then f double prime is going to be 2x to the negative 3. Okay, then f triple prime is going to be negative 6x to the negative 4. All right, so that will give us what we need for P3. Now we're centering this around 1, so thankfully that actually ends up being okay, because when we plug 1 into all of these, the x thing just becomes 1. Right, so f of 1 will be 1. F prime of 1 will be negative 1. F double prime of 1 will be 2. And f triple prime of 1 will be negative 6. All right, and then let's do this over here. We have all the stuff we need now. So p sub 3 of x is going to be 1 minus 1 times x plus 2 over 2 factorial times, and I've already made a mistake. It's not 1 times x, it's 1 times x minus 1. plus now 1, the f double prime, which is 2 over 2 times x minus 1 squared, then minus 6 over 3 factorial times x minus 1 cubed. So I'm just going to go through. This is our f of 1. This is our f prime of 1. This is our f double prime of 1 over 2 factorial. This is our f triple prime of 1 over 3 factorial. Well, 3 factorial is 6, so actually each one of these just becomes a 1. So while this seemed on the outset kind of nasty, it actually turns out all right. We're going to get 1 minus x minus 1 plus x minus 1 all squared minus x minus 1 cubed. And actually from this pattern we could probably theorize that the next terms, if we wanted to keep going, we'd probably get an x minus 1 to the 4th, and then minus an x minus 1 to the 5th, and then a plus x minus 1 to the 6th if we decided to keep going. All right, so I think that would be a good exercise for you to try to see if that does continue in that pattern. Okay, now let's use this to approximate. Let's do 1 over 1.05. So this would be f of 1.05. All right, so here's what I got with my calculator, 0.9523809.524. All right, now let's look at P3 of 1.05. Well, when we plug this in, that 1's not going to change, and we're subtracting 1 at each one of these. So the 1.05 minus the 1 is going to give us just 0.5. Any little thing you can do to simplify your work here. Okay, so let's see what we get here. And I just realized that these should be 0.05s. It's getting too excited, I guess. All right, so my calculator, calculating this gave me 0.952375, which we can see is really close to what we got with the calculator. In fact, I went ahead and calculated the absolute error here. The absolute error is 5.95 times 10 to the negative 6. So that's basically accurate within about 5 decimal places. All right. Okay, let's look at another one. Okay, so for this one, we're looking at f of x equals the square root of 1 plus x, and we want to find the degree 4 Taylor polynomial with a equals 0. So thankfully, we consider this around 0. If this was just, I'll show you, if this was just the square root of x, we wouldn't be able to center it around 0 because after our first derivative, we'd get 1/2 times x to the negative 1/2, and we can't plug 0 into that. So if it was just the square root of x, we couldn't center it around 0. Thankfully, though, it's actually square root of 1 plus x, so we can center it around 0. Is that going to be more work with this 1 plus x? Well, I don't know about that. It's probably the same amount of work, but to me it feels nicer to not have to put x minus 1s at every step, you know, that kind of thing. So anyway, I'm going to rewrite my f of x as 1 plus x all to the 1/2. That'll be a little nicer. I'll also say when we do the our derivatives, we have we'll have to do chain rule, but thankfully chain rule will just give us 1 since the derivative of the inside is 1. So we don't really have to worry that much about it. Okay, that's one nice thing. So I can just say, all right, this is 1/2 times 1 plus x to the negative 1/2, and move on to the next one. All right, so this will now be negative 1/2 times 1/2, so that's times 1/4 times 1 plus x, okay, to the negative 3/2. And then the third derivative will be negative 1/4 times negative 3/2, so the negative will disappear. Okay, times 1 plus, okay, well, whatever, 1 plus x to the negative 5/2. And then the fourth derivative will be, we'll get the negative again, it'll be 1/4 times 3/2 times 5/2 times 1 plus x to the negative 7/2. All right, now at this point, we're plugging in 0, and every time we plug in 0, well, these will go away, and then we're just left with 1s. So the x to the power stuff just goes away. Okay, so that tells me that f of 0 is just 1, f prime of 0 is 1/2, f double prime of 0 is negative 1/4, f triple prime of 0 is let me call that 3/8. I don't think we'll be able to simplify this in a nice way. Maybe we will, but I'm not feeling it. And then this will be 15 16ths. Yes, 15 16ths. All right. Now, when we put it in our formula, don't forget that we still have to divide it by the factorial. So I'm actually going to multiply by 1 over the factorial when I do this. So this should be 1, then plus 1/2 times x minus 1/4 times 1 over 2 factorial times x squared. Okay, plus 3/8 times 1 over 3 factorial times x cubed, then minus 15 16ths times 1 over 4 factorial times x to the 4th. And some of these things will simplify because we have this 3 here, and that will get rid of the 3 down here in this factorial. And then we have a 3 that will cancel with this one. So let me simplify it down just a bit. This isn't necessary. This is probably good enough if you need to use it to approximate. This will be 1/16 x cubed. Then this one will be 5/32. Okay. Now, before I leave you to get started on the homework, I wanted to show you the nicest Taylor polynomials we have, which is for e to the x. Right, for e to the x, every derivative of e to the x is itself. And if we let a equal 0, then for every derivative, when we plug in 0, we get e to the 0, which is 1. So for all n, for all k, the derivative, nth derivative at 0 over n factorial is just going to be 1 over n factorial. Okay, so the Taylor polynomial for e to the x is basically it's 1 plus x squared over 2 plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus x to the 6th over 6 factorial, x to the 7 over 7 factorial, on and on and on until we get to x to the n over n factorial. All right, this I consider the Platonic ideal of the Taylor polynomial because it really simplifies pretty much everything down to just the basic pattern, and that's because every derivative of e to the x at 0 is 1. Okay, now some of these terms might look familiar. In fact, you may recognize 1, and x squared over 2, and x to the 4th over 4 factorial, and x to the 7th over 7 factorial. You might actually recognize that from when we did cosine. In fact, cosine of x takes the even terms of the e to the x and alternates them. Okay, and say that would be P12. Okay, but cosine is the even alternating from e to the x, and when you go through it, I suggest trying this yourself, but when you go through it, sine is going to do similar, except it will alternate the odd ones. Right, and this one would be P11. So sine is the odd alternating, and both of these are from e to the x. It's actually kind of fascinating that they're so closely related. Okay, so these are some of the important Taylor polynomials, and you'll come across quite a few of them when you tackle the homework. So anyway, I think that's good enough for this particular video. So I will catch you all on the next one. Cheers.